Last video here for chapter 5, looking at 5.7. This should be really short. This is going to be an example with electrical systems. We've already done some examples in the past. I think it was in chapter 3 where we did those RL circuits and then those RC circuits. Now we're going to be doing all of them together, an RLC circuit. So just remember that the R stands for resistance, the L is the inductance, and then the C is the capacitance. I'm going to go over to the book here just to show you a picture of the circuit we're dealing with. So here's going to be our battery or our voltage source. It's outputting charge. Then we're going to have a resistor, we're going to have our inductor, then we're going to have a capacitor here. And we kind of talked about what these three different things do in a circuit. It's just that we've never had them all together. So let's look at the differential equation that would come out of this. Before we jump into that, I guess, there is some numbers that I want to throw in. We're going to start our battery outputting 100 sine t as the electricity going through the system. We're going to have our resistor be 0.02. Remember, this is in ohms. We're going to have our inductor be 0.001. This is in henries. And then we're going to have our capacitor just be 2, and this is Faradays or farads. Okay, so if the initial current and the initial charge on the capacitor are 0, then what we want to do is we want to determine the current in the circuit at time t. All right, so that's the problem. Okay, so just setting it up, and this is mostly stuff that we've seen before. So first things first is that we get the current by taking the derivative of the charge. And then other stuff that we should have seen before is that we looked at the this E, which is the electric force. This voltage that's going across the system. So E sub C is going to be the charge divided by the capacitance here. So that's the voltage going across the capacitor. We have E sub R, the voltage going across the resistor. That's just R times I. That's coming from that very famous, what's it called? Ohm's law? That doesn't sound right. Something like that. And then we have the voltage going across the inductor. That's going to be L times I. Okay. If we take all of these together, the voltage across the capacitor, voltage across the resistor, plus the voltage that's going across the inductor, this is going to just add up to the total voltage of my circuit. All right, so now we can just plug in all these different values. So it's going to be this first one here, E sub C. I'm going to put it at the end and just kind of rearrange it some. You'll see why here in a minute. Oh, I also messed up here. Sorry about that. This should be the derivative of I. So the voltage going across the inductor is the inductance times the derivative of the current. Okay, I'm going to put that one in front. So Li prime, the voltage across the inductor, plus R times I, the voltage across the resistor, plus I'm going to write this as 1 over CQ. That's the voltage that's going across the capacitor. And that's going to be equal to E of T, which is the voltages going into the system. Okay, so what we want to do now to be able to get this to something that this Q is out of the way is that we're going to differentiate both sides. We're going to differentiate, that way I can plug in I as Q prime. All right, so now we're going to get the equation Li double prime plus Ri prime plus 1 over C, and then Q as a derivative is just I. And that's going to be equal to the derivative of E of T. All right, and if we plug in all of our given conditions, we're going to get this. So the inductance, 0.001 I double prime, plus the resistance, 0.02 I prime, plus 1 over C, which is going to be 1/2. I'll just leave this as a decimal, so 0.5 times I, and that's going to be equal to the derivative of the incoming voltage, which is the derivative of sine 100t, which is going to be 100 cosine 100t. Okay, I don't really like these decimals here, so I'm going to get rid of that just by multiplying everything by 1,000. So it's going to be I double prime plus 20 I prime plus 500i is equal to a pretty big number over here, 100,000 cosine 100t, just to get rid of the decimals. All right, and now what we have is we have a second order non-homogeneous equation. And if we want to solve this, first thing we need to do is to solve the homogeneous part. And to solve the homogeneous part, remember this is the auxiliary stuff. So just real quick, that's going to be r squared plus 20r plus 500 is equal to 0. This is going to have solutions. You would just plug this into the quadratic formula, and it should spit out this. So r is going to be negative 10 plus and minus 20i, which means that we're going to have a homogeneous solution of c1 e to the negative 10t cosine of 20t, and the same thing with sine. So plus c2 e to the negative 10t sine of 20t. Okay. Then we have to find the particular solution. Since we have a function on the other side, we're going to use the undetermined coefficients thing here, which means that we need to come up with a potential particular solution. On the right-hand side of my differential equation, we have this, 100,000 cosine 100t. If I'm using the undetermined coefficients, I want to set my particular solution to be something similar to this. I do not have a polynomial out in front. I do not have an e function, but I do have this cosine. So this is going to be the second part of undetermined coefficients, but a very simple case. We're going to set this just to be a constant cosine 100t plus a constant sine 100t. Remember, now we want to take this and plug this in to my differential equation, so we're going to have to take the derivative twice. The derivative the first time is going to be negative 100a sine 100t plus 100b cosine 100t. Take the derivative again. That's going to give us negative 10,000. I think that's right. A cosine 100t minus 10,000 b sine 100t. Okay, now taking these and plugging these into my differential equation, we're going to have the second derivative here, so negative 10,000 a cosine of 100t minus 10,000 b sine 100t. All right, it's going to be that plus 20 times the first derivative, negative 100 a sine 100t plus 100 b cosine 100t. Okay, and then that plus 500 times the function itself, a cosine 100t plus b sine 100t. And that's all going to be equal to the right-hand side, which is 100,000 cosine of 100t. All right, so it's pretty awful, and there's a lot of big numbers here, but we can combine the like terms together. So we have some a cosine 100t's, b sine 100t's, a sines, and then b sine somewhere. Yeah, down here, a b sine. So we're just going to combine all of these like terms together. I might need to get my calculator out for this stuff. So I have an a cosine 100t, and then down here an a cosine 100t. And I think that's the only ones that I see. So it's going to be negative 10,000 plus 500, which is negative 9,500. And it's going to be a cosine 100t. So now these two are gone. I have, let's find the b cosines. I think I just have the one over here. So it's going to be that 100 times 20 plus 2,000 b cosine 100t. Okay, so those are the cosines done. We're going to have the sines. The a sines, looks like I only have the one here, so negative 2,000 a sine 100t. And then the b sine 100t's, I have this one, the negative 10,000, and then I have the plus 500 again. So negative 9,500 b sine 100t. And that's still equal to the right-hand side, the 100,000 cosine 100t. Okay, If I want to find my a and my b here, we're just going to set the cosine coefficients all equal to each other, and then the sine coefficients. So if I'm looking at the cosine coefficients, I have negative 9,500 a plus 2,000 b, and that's going to be equal to 100,000 on the right-hand side. If I'm looking at the sine coefficients, I have a negative 2,000 a minus 9,500 b, and that's going to be equal to 0 on the right-hand side. All right, we have this system of equations here. This is not hard to solve. You could do a substitution, or you could try to do some elimination stuff. Just solve maybe this second equation for a, adding the 9. I'll write it all out. So we're going to have a is equal to 9,500 divided by 2,000, whatever that number is, b. Substitute this in for the a here, and then you would solve for the b. So I have the answers written here. A ends up being, these are some pretty awful looking decimals. I think these are rounded. A is negative 10.080. B would come out to be 2.122. So they're not nice numbers, but easy to solve this system here. Okay, but now that we have that, that means we have our particular solution, because our particular solution is now going to be negative 10.080 cosine 100t plus 2.122 sine 100t. All right, and that means that I have my full solution, because my full solution is just taking the homogeneous and the particular and adding them together. So we're going to have the C1 e to the negative 10t cosine 100t plus C2 e to the negative 10t sine 100t. And then that's going to be plus the particular solution, negative 0.10080 cosine 100t plus this 2.122 sine 100t. Oops. Last little thing that we would need to do is to figure out what these constants are based on the initial conditions. Remember that we kind of wrote out the initial conditions to begin with. My starting current is at 0. Also, the derivative of the current is 0. So it's not obvious that this derivative is 0 necessarily, but you can figure that out just based on the initial condition or the statement that was said at the beginning there. So this is, I'll put it in parentheses here, using that initial equation Li prime plus Ri plus 1 over CQ is equal to that E that we had. So if you plug in everything that you were given and solve this for the derivative of I, you're going to get that the derivative of I has to equal out to be 0. So it's not hard to see. All right, but plugging all that stuff in, taking the derivative here, so we're going to have to take the derivative of all of this stuff, which is going to get kind of gross, because we're going to have to do some product rules here. This is not something that I would ever ask you to do necessarily, but we'll write it out anyway. So here we go. So the derivative, it's going to be the first C1 e to the negative 10t times the derivative of the second, which is going to be negative 100 sine 100t. That plus the second cosine 100t times the derivative of the first, which is going to be a negative 10 e to the, negative 10 C1 e to the negative 10t. Cool. All right, so that's just the derivative of this first term. That plus derivative of the second term, C2 e to the negative 10t times the derivative of sine, which is going to be 100 cosine 100t. That plus the second sine 100t times the derivative of the first, which is going to be, again, oh no, no, come back to me. Come back to me, Word. You can do it. You can come back. Oh, it's gone. Is it going to make it? Come on, everybody, pray. All right, we're good. Oh, that's never happened before. All right, it turns out that typing in Word may not be the best idea. Oh, man, I almost had a heart attack. Okay, great. So what were we doing? We did the derivative, first derivative of the second, and our second derivative of the first, which is going to be the negative 10 C2. Ah, crud. Now I'm all flustered. Nothing's going to work right. Negative 10 C2 e to the negative 10t. All right, that, and then these things derivatives. So we're going to have negative that 10.080 times negative 100 sine of 100t plus 2.122 100 cosine of 100t. All right, and that's all equal to 0. And also remember, we're plugging 0 in for the t's at this point. All right, so we're going to get 0 is equal to, I guess we should decide which initial condition we're going to do first. Let's just do the regular one. I of 0 is equal to 0. So that's going back up to this equation up top here. Okay, great. So we're going to get 0 on the left-hand side is equal to, if I plug t to be 0 into this first term, e to the 0 is just 1, cosine of 0 is 1, so I just get the c1. Plugging 0 into here, I get 0 because of the sign. If I plug 0 into here, I get that negative 10.080. If I plug 0 into here, I get 0. So all of this just to say that my C1 is going to be positive 10.080. Okay, if I do the derivative thing now, so I prime of 0 is equal to 0. Plugging into the left-hand side of this equation, we get 0. If I plug 0 in for the t for this first term, because of the sign, the whole thing is 0. If I plug 0 into the second term, I'm going to get a 1 for the cosine, this negative 10, and then the c1. And then, of course, e to the 0 is just 1. If I plug it into the second term, I'm going to get that 100 c2. Again, the e just goes to 1, cosine of 0 goes to 1. Plus down here, that's all going to be 0 because of the sign. Plus that's all going to be 0 because of the sign. And then over here, we're going to get 2.122 times 100 for the very last term. All right, so if you plug in the C1 that we just found from here and get the C2 by itself, C2 comes out to be negative 5.570, according to my calculator. Okay, and that's it. So now we can write out our thing. So my final current I is going to be kind of gross looking, 10.080 e to the negative 10 t cosine 100t. And that's going to be minus 5.570 e to the negative 10t sine 100t. That minus 10.080 cosine 100t plus 2.122 sine 100t. Okay, it's an awful looking solution here, but that is going to be the solution for the current in our system. Notice that the terms that have the e to the negative 10t's are eventually just going to go to 0. So these terms out front is just going to give us some kind of weird waves to begin with, but eventually these last two terms are going to be the ones to take over. Let's see if they have the picture of our solution here in the book. I kind of doubt it. Oh no, they just go straight into another example. Let me try to figure out how to graph it just real quick. Give me a second. Pausing. Okay, so I tried typing this into Desmos and it flipped out. So here's what Desmos is spitting out for me. Don't worry about what's going on the left-hand side of 0, just the right-hand side. So it looked kind of awful, but if you zoom in really, really far, you can tell that they are actually like up and down lines that are going here. I can tell now why the book didn't actually graph this, because it's you can't. What's this called? The frequency is just so small and such a high amplitude that it kind of looks like it's just a filled in line for my waves. But do notice that like right here, you see this little empty space? That's because initially we have a smaller amplitude. It's only until we get to about 1, which I know isn't all that great, that we do get like our other terms just kind of taking over. But initially it kind of struggles to get going. It struggles to get going because of the inductors taking a while to boot up is not the right term, but I don't know, boot up, I guess. So there we go. 5.7 and chapter 5 in total done.